right, guys, welcome to chemistry. We're excited to get going today. Last time, Mr. Knappenberger mentioned that we will be continuing our discussion on equilibrium, but today we'll be taking a mathematical focus. So because of that, you will want to have a paper, pencil, and your calculator for today's notes. All right, here we go. Equilibrium expressions. Let's do this. Before we jump into just the math and such, we need to take a look back to the concepts that we learned last time. Last time we looked at reactions like this one, where we have our acids that react with a base to then form the conjugate base and the conjugate acid, right? But we noticed that the arrows in the center were different. The arrows in the center show us that there's a forward reaction and a reverse reaction. Knowing that, this tells us that while these reactants are forming products, these products are also reacting together to form reactants. It kind of forms this circle going back and forth and happening at the same time. And we get a reversible reaction that doesn't have an end. It just continues going on and on and on. In fact, we also learned that these forward reactions and the reverse reactions have some things that are similar and some things that are different, right? We learned that the forward reactions might be more sensitive to temperature and surface area than the reverse reactions. And sometimes the reverse reaction would be more sensitive than the forward reaction. Because of that, we want to have a greater understanding of what is actually going on. And it's going to continue this way where the reactants form the products and the products form the reactants until we reach a state called equilibrium. Equilibrium is a state at which the forward and reverse rates are equal. So the speed at which the reactants are forming products and the speed at which the products are forming reactants is equal. Those rates are the same. And when we hit that, we're at equilibrium. Then we also know that at equilibrium, the concentrations of our reactants and our products are constant. Concentrations are constant. They are unchanging. If you remember back on the demo that Mr. Knappenberger did, you remember seeing that we had that reactant graduated cylinder and the product graduated cylinder, right? And it ended up with a ratio of 70 to 30, right? 7 to 3. As he was transferring water from one to the other, right? Now, if you remember right, he was transferring them at the same time. Eventually, the water in the tubes as he transferred reactants to products and products to reactants was the same, which told us that rate was equal. But at equilibrium, that ratio of 7 to 3 was constant. That was unchanging. That ratio represented the concentrations. So we know at equilibrium, the rate of the forward reaction and the rate of the reverse reaction is equal. And then the concentrations of my reactants and the concentrations of my products is constant. They aren't the same, but they're unchanging. Okay? So we saw this ratio here. Products over reactants, the ratio of 70 to 30, that 7 to 3 ratio. Guys, this is where we're going to derive the math from. This ratio has a name, okay? It's not a 7 to 3 ratio for every reaction, but we want to know how to calculate this ratio for each equilibrium reaction that we come across, okay? The name of this ratio is the equilibrium expression, or Kc. Okay, so this is that ratio. Okay, really all it is the mathematical ratio of products to reactants when a reaction is at equilibrium. As soon as it hits that state where the forward and reverse reactions are equal and the concentrations are constant, then we can calculate the equilibrium expression, Kc. This is what it looks like. You'll want to get this in your notes. Kc, here's what this means. K stands for equilibrium, okay? And so at equilibrium, we know that this is the ratio of products to reactants, okay? Then C stands for concentration, just like these brackets here stand for concentration, okay? So you can see that this ratio is just products over reactants, just like our 70 to 30, right? Just like what we saw in that demo. So when we write this out, really, it's just the right side of the reaction over the left side of the reaction. It's kind of important to keep that straight because in a reversible reaction, you know, our products are technically reacting, right? But our products are always going to be the things on the right side of the equation. Our reactants will always be the things on the left side of the equation. So I'm going to show you an example of how this is written. If we have this equilibrium equation here, you can see I've got 4BF3 plus 3H2O in equilibrium with H3BO3 plus 3HBF4. Okay? If I want to take this equation and write its equilibrium expression, this is what it will look like. Okay? I'm going to show you what it look like, and then we'll figure out how we got from one point to the next. We'd write Kc equals, and then on top, I'm going to put the products, right? The stuff on the right side. I'm going to put this on top. Watch how that goes. Like so. Okay? And then on bottom, I'm going to put my reactants. The stuff on the left side. That's this stuff. Watch how it goes. Okay? Like so. All right, now let's notice a couple things. All right? 3 things to notice. Number 1, stuff on the right goes on top. The stuff on the left goes on bottom. We just went through that, okay? We want to keep that in our head. Products on top, reactants on bottom, okay? The next thing I want to point out are these exponents here. Where did these come from? Where did that come from? Okay. Now if we notice, let's focus just on our products for a second. If I focus on just on this part, I can see that this has an exponent of 1, right? Just like this has a coefficient of 1. Remember, if it's empty, if there's nothing there, we assume that there's a 1, just like you can in math. This has an exponent of 3 because this has a coefficient of 3. So I can see my coefficients became exponents, right? Now let's check. It does it on the same thing. It does the same thing on the reactant side, right? I have my reactants. They went on bottom. Now look, my coefficient here becomes an exponent there. My coefficient here becomes an exponent there. Okay, we good with that? Okay, so that's the second thing to notice. Where did these coefficients go? They become exponents. Okay, the last thing to notice when we're writing these equilibrium expressions, okay, is this. Notice, let's start on our product side again. Start on this side and we'll look on top first. Okay, notice, in the reaction, this is a plus sign. But in the equilibrium expression, they're multiplied. Okay, remember, if there's nothing there, it's assumed that they multiply, right? So the pluses become multiplication. And here, again, that plus became a multiplication. Are we good? Let's try this out. Okay, we are going to try writing an equilibrium expression. Okay, so if I've got this equilibrium reaction, we want to figure out what the equilibrium expression is. Okay, that is Kc. So I'm going to write Kc equals, and then think to yourself, what goes on top? Reactants or products? Products goes on top. Products are the stuff on the right, so this is going to go on top. Okay, and then I know that this, my 2 here, becomes the exponent, so it's going to look like that. Then for the bottom, I'm going to take my reactants. I know that my coefficients become exponents. I know that my plus sign becomes a multiplication, so it should look like this. So far, so good? So we can see that it just follows those 3 rules. Whatever's on the right goes on top. Products go on top. Reactants go on bottom. And then coefficients become exponents, and then plus signs become multiplication. And then we have our equilibrium expression. But as promised, this isn't just writing out the expression. What we created is really a formula that we can use to figure out different things about the equilibrium reaction. Okay, so for example, we can figure out things like this. If the final concentrations of this reaction at equilibrium are SO2 equals 0.125 molar, O2 equals 0.11 molar, and SO3 equals 0.20 molar, what is the Kc for the reaction? Okay, so we can solve for Kc. We can figure out what that number is. All right. Now, in order to do this, what I would want to do is, first of all, write the equilibrium expression, which we just did. Awesome. Okay. And then the next thing we want to do is just start to plug in the numbers. Okay. I can see I've got SO2, okay, that I would plug in right here. I've got O2 that I would plug in right there. And then I've got SO3 that I would plug in right there. And being the organized, clear communicators that you are, you would first write your equilibrium expression, and then you would start to plug the numbers in. You would actually take the number that we found, right, for SO3 right here, and you would plug it into the equation. You'd take the number for SO2 right here, and you'd plug it in, and the number for O2 right there, and you'd plug it in right there. Okay. Now you're ready to put this in your calculator. All right, so I'd grab my calculator, I would put 0.2 squared divided by, and then I would put this whole thing in parentheses when you put it into your calculator so that the order of operations works correctly. Then divided by, put it in parentheses, 0.125 squared times 0.11, close parentheses, hit equals, and you should end up with Kc equals 23. Okay, so if you didn't end up with 23, you'll want to double check how you put this into your calculator and make sure you're putting it into your calculator correctly. But also I want you to notice that we do check our Sig Figs here, right? So let's double check our Sig Figs. I have 2 Sig Figs in this number, 3 Sig Figs in this number, 2 Sig Figs in this number, so I'm limited to 2 Sig Figs, which is why Kc only has 2 Sig Figs. Good? Okay, also notice Kc does not have any units. There's no units for Kc because this is just a ratio. But that also means that it's kind of hard to tell what Kc actually means. What does it mean that Kc is 23? Okay. Well, if we think of our ratio, we remember that our ratio is a ratio of products over reactants. Because of that, even though there's no units here, this value can give me some information about the relationship between the products and reactions in this equilibrium. What does this tell us? If this number is 23, it tells me that there's more product than reactant. Anytime Kc is bigger than 1, that means I've got more products than reactants in this equilibrium. Okay? And then the opposite would be true. What if it wasn't 23? What if this came out to be like 0.128, right? That tells me that there's more reactant than product, right? Because this number on bottom would be bigger than the one on top. Okay? So again, if Kc is less than 1, there's more reactant than product. Notice it's not negative, it's just if it's a decimal, all right? And that can be helpful for other applications as you study further into equilibrium. Okay, guys, we're going to do one more example, and then we're going to get you set to do your homework, and you'll be ready to do a lab when we come back to apply this stuff. Okay, here we go. If you have this equilibrium right here, this equilibrium reaction, can you write the equilibrium expression? Take a second and try it out. What would be the equilibrium expression for this reaction? I'll give you a couple of seconds. Okay, let's check this out. Remember, it's products over reactants. It's right over left. So I'm going to take the compounds on the right, and I'm going to put them on top, like so. Okay, and then I'm going to take the products on the left, right here, and I put them on bottom like so. I make my coefficients an exponent, and I make my plus signs multiplication. Okay, so your equilibrium expression should look like this. Okay, now let's use this to solve. Here's our example. If the Kc for this reaction is 0.39 and the final concentrations at equilibrium for H2 is 0.20 molar and I2 is 0.18 molar, what is the concentration of Hi at equilibrium? Okay, so notice in this case, we aren't solving for Kc, we're solving for the concentration of Hi. So I'm going to take the numbers that I know and plug them into this equation so that we can solve for Hi. All right, I know that Kc is 0.39, so I'm going to plug it in right there. I also have the concentrations for H2 and I2, so I'm going to plug them in on top. And then I don't know Hi, that's what I'm solving for, so I'm just going to make it x squared. I'm just going to replace this, what we're solving for, with x. All right. At this point, we're going to do some algebra to solve for x. So first of all, I need to get x on top, right? So if you remember, right, when it's on bottom, I've got to multiply by x squared on both sides. That way this cancels, leaving me with 0.39x equals this side. I just plugged this into my calculator to get this one. And now I need to get x alone. Okay, to get x alone, I've got to do the opposite of this, right? To get this onto the other side. So this is being multiplied by x squared. So I'm going to divide it by 0.39 and divide this by 0.39. That cancels this out, leaving me with x squared. Okay, and then I plug this into my calculator, and I see that x squared is equal to 0.092. And now I've got to get x completely alone. Right now it's being squared, so I got to do the opposite on both sides to get x alone. So if it's being squared, I need to take the square root on the left, the square root on the right, and I'm left with x equals 0.30 molar. Okay. Now remember, this one has molarity as its units because we're solving for the concentration of Hi. So pay attention for what you're solving for. Really, if you can get the equilibrium expression and if you can plug in your numbers, it's just some algebra to be able to solve for any part of this equilibrium expression, and then you can figure that out. So we can see that that concentration of Hi was not too intense. All right, very good. Guys, that's it. That's really all you've got to be able to do. And then you are able to take what we've learned about equilibrium and apply the math to it. Okay, so would you do me a favor and pull out your homework? Take a look at that. There's one of the homework questions that I want to point something out on. On homework 1D, it asks you to write the equilibrium expression for something we've never seen before. Okay, it asks you to write the equilibrium expression for this reaction. Okay, now some of you may have already noticed the part that looks a little different here. All right, the right looks normal. We're used to that. We're now used to an equilibrium arrow too. That's totally fine. But did you notice that right there? We have never seen something like copper 2 sulfate multiplied by 5 waters. What does that even mean? Okay, well, let me tell you. Okay, this right here is actually one reactant. That is one reactant. It sticks together. This is actually copper 2 sulfate that's been hydrated. Now what that means is that we've got the copper 2 sulfate compounds that are organized in their structure, just like salt organizes into a specific structure. But when you hydrate it, what happens is you start to shove waters inside of this structure that is set up here. So for every one copper 2 sulfate molecule you have, you've got 5 waters shoved inside the structure. It looks kind of like this. Okay? So can you see, let me get a color that might stand out a bit. Let's try this one. Right here, I've got this copper 2 sulfate, copper 2 sulfate, copper 2 sulfate. I can see the structure. Copper 2 sulfate, copper 2 sulfate, copper 2 sulfate, copper 2 sulfate, copper 2, all the way through. I can see that structure. But then you can also see that inside, in between the copper 2 sulfates, there's a ton of water that has been added in. And if you count it out, that ratio is 5 to 1. For every 1 copper 2 sulfate you have 5 water molecules shoved inside of there. Okay? So when you write this out, when you're writing these equilibrium expressions, okay, this right here, this is just one reactant. It sticks together as one compound. Okay? And then you would write out this part just like normal, like we're used to. Okay, guys, I hope that helps you out. Do your work. Be careful about showing your work and expressing your thoughts mathematically very clearly. Check your answers as you go, and we're excited to see you soon. Thanks. Bye.